Here's our first example using component forces to calculate an unknown force. There's a lot going on here. This is the first one, so try to follow along with this. First step is a force diagram showing the forces acting on the cart. That would be just gravity straight down, normal force perpendicular to the surface of the ramp, so you see it goes off at an angle, and the tension force of the string pulling on the cart along the line of the string. We're going to want to do net force equations to add up x and y forces, so I need to draw x and y axes. Normally we've been doing straight up and down y, left and right x. I'm going to draw this y-axis parallel along the normal force here. And that means since it's the normal force and the tension force are at right angles, the tension force will have the x-axis along it. So this is the x-axis and this is the y-axis. Why that's done is it makes this problem easier, and we'll do this frequently with these kinds of problems. Now I only have one force that's not on the x or y-axis and two of them that are. So it's more work when you have forces not on the x or y-axis, so we do it this way to make it easier. For clarity, I've now enlarged the force diagram from what it was. Here's the new part. This force, the gravitational force, is not on the x or y-axis. We want to get its components. Two separate component forces that comprise or make up this one force at an angle. And so what we do to do that is we project down to the x-axis here from the point, make a right angle, and that means from here to here is represents the x component of this force, and I will call this gravitational force x for x component. And then do the same thing, project down, make a right angle with the y-axis, and that makes this the y component of the gravitational force, like that. Now I am going to move that last vector over here so I can see a nice right triangle. And it's the same vector. It has the same length and the same angle, so they're equal. And I will take away right here so it doesn't confuse us. And I now have a right triangle to work with, and I will relabel this FGY. And I'm going to want to know that the magnitude of these forces. It's also important to realize that when we turn the axes from straight up for y, we rotated it 18 degrees that way. So that makes this angle right here 18 degrees, which means this angle right here is 18 degrees in this right triangle that we're going to be working with. Now here's the right triangle that's important to us. We now have an angle, but I have nothing else. I know that this is the x component of the gravitational force, this is the y component, and this is the gravitational force. And I can calculate what that is so I can know the side of that right triangle. Let's do that. We know that this gravitational force is equal to the mass of the object times the gravitational field strength, which in this case equals 0.25 kilograms times 9.8 newtons per kilogram, which equals 2.45 newtons. So that means my right triangle, I now know the hypotenuse value, and I know this angle, and we can figure out anything we want about this arrangement, which means we can figure out these components, which is what we need. So I have this equation that allows me to calculate FGX, the x component, and this equation allows me to calculate FGY. I'm using the 18-degree angle there and the trigonometry. And I see that FGX here equals 0.76 newtons and FGY equals 2.33 newtons. So I can put them in the diagram and realize that FGY I can bring over and put on the y-axis. It's parallel to the y-axis, and that's its length. So that would have a value of 2.33 newtons right there. And now the net force equations will help us solve for the sum of the forces along the x-axis are just the tension force plus the x component of the gravitational force. And when I put in what I know that these forces must be balanced because it's not moving. The tension force I don't know, but I want to know, and I now have figured out that the x component of the gravitational force is 0.76 newtons. Therefore, the tension added to that must be 0, so the tension force must equal minus 0.76 newtons. So that is the calculation for the tension force acting on the cart. And when we tested in class, it came out to be exactly that.